Let us have a discussion on transformers. Transformers are crucial for step up and step down voltages. These two processes are vital for efficient transmission of power over a long distance and safe distribution at the local area. This is a symbolic representation of transformer. Pictorial representation. Symbolic representation of transformer. There are two coils. These two coils are inductors. Two inducting coils. There is a coil, there is a coil. The electric power is transferred from one coil to another coil without electrical connection through magnetic material. Electric power transmission. Electric power is transferred from one coil to other coil without an electrical connection, but through magnetic material, that is a soft iron core. Energy or electric energy is transferred from one coil to other coil via magnetic field. The iron core produces a strong magnetic field. Here, electric energy is converted into magnetic energy. Then magnetic energy is getting converted into again electric energy, pass on to the secondary coil. This is the transformer. The name applies transformer. Energy transfer from one coil to other coil is transformer, not directly through the conductor. So this is what the symbol of transformer. Let us have a design of a transformer. That is a kind of design. Suppose an efficient design of a transformer. The construction is, it is a soft iron core. That is a soft iron core taken in the shape of square or rectangle. Soft iron core. At the one side, the coil is wounded in multiple turns. Let us call this as primary coil. On the other side, one more coil is wounded with multiple turns. It is called as secondary coil. Primary means which supply the power. Secondary means which receives the power. Secondary coil. Now the primary coil is here. Let us pass electric current through the coil. When you pass electric current through the coil, magnetic field is induced along the axis of the coil. On passing electric current, it induces magnetic field along the axis of the coil. Electromagnetic induction. So this power transmission or power transfer is by the electromagnetic, by the principle of electromagnetic induction. This requires AC current. For a functioning of transformer requires AC current. Why AC current? AC current is variable. Of course, it is variable in magnitude or direction. But this principle won't work with the DC current. DC current is not a variable current. Therefore, we have to apply AC source, AC current to the coil. On passing electric current, AC current, variable current in the coil. As the current flows, magnetic field is induced along the axis. And if the current varies, if you have variable current, we get variable magnetic field. In other words, variable magnetic flux. Flux means total magnetic field is called as flux to the material. Since it is wounded over the material, these magnetic lines always induced in the material, the iron material. And this iron material is a good conductor for magnetic field or magnetic field lines. Very good conductor. Once the magnetic lines are induced in this, that is induced along the axis, it is in the material, iron material. These are getting concentrated and condensed in the material only. The magnetic lines, of course, will not spread out because the material has high magnetic permeability. Will not allow magnetic lines to go out of the material. All magnetic lines are getting concentrated and they will flow through this conductor, very good conductor. So it is spread. Magnetic flux spread through the material, pass through the material like this, magnetic flux. All over the material is through entire material. So this magnetic flux is variable because current is variable, magnetic flux is also variable. So we see the material as variable magnetic flux. This soft iron core has variable magnetic flux. What is meant by variable magnetic flux? Rate of change of flux with time. That is d pi by dt. Flux, pi stands for. Rate of change of flux with time is called variable magnetic flux. Where there is a variable magnetic flux in touch with any conductor or coil, induces EMF, induces voltage. It is called as induced voltage, and current also, induced current. So this variable flux, magnetic flux, is in touch with the coil, this coil as well as this coil, and induces the voltage or EMF in the same coil, here in the coil. This is called as self-induction. This is called as mutual induction. The flux induces voltage in the same coil is called as self-induction. The flux what is induced by the coil is induced current, induced voltage in the other coil is called as mutual induction because the flux is in contact with this coil. The magnitude of flux induced. The magnitude of flux induced is given in accordance with Faraday's law. That is what I call these parameters as voltage applied to, that is called as primary coil. P stands for primary, voltage, current and number of turns of the primary coil. Voltage, current and number of turns of the secondary coil. Here. The voltage induced in the primary coil is also called as self-inductance, equals minus because of opposite direction. Depends on the number of turns of the primary coil and rate of change of flux in the primary coil. That is Faraday's law. We call it Faraday's law. and voltage induced in secondary coil is again minus, opposite to, that is in the opposite direction. Number of turns in the coil and the rate of change of flux in the secondary coil. Yes, this flux variation is almost same. There may be a little difference between these two values. This is called as self-induced voltage. This is called as mutual induced voltage. This self-induced voltage is same as the voltage applied, AC voltage applied in magnitude. What is induced is same as voltage applied. It is in magnitude, not in direction, because they are in opposite direction. The voltage applied, voltage induced are in the opposite direction. But magnitude remains same. And the induced voltage, it is called as voltage output. Output voltage. Here input voltage. Voltage at primary, voltage at secondary. Output voltage, input voltage. That is what the flow magnetic, that is actually what is that during this process of what is that when the current changing into magnetic flux. Here it is a change of electrical in terms of energy. Electric energy changes into magnetic energy, then magnetic energy changes into electric energy. Here input, output, electric energy input, electric energy output via magnetic field. That is what here the principle or the basics involved in the transfer of power from here to here. These are variables. I say that parameters are actually different. They found very so they found at different values during the process of transfer power. These variables we take in the form of the ratios. That is the ratio of the voltage, ratio of the number of turns, ratio of the current. Secondary voltage, primary voltage. Secondary number of turns in primary voltage. There primary current, secondary current. Because voltage and current are inversely related. This ratio, that is with the differences, what difference you are finding, this ratio is called as transformation ratio. Okay, transformation ratio. This value plays an important role for designing the transformer, type of transformer. For a step-up transformer, the value of K should be greater than 1. Here the ratio, the value of K should be greater than 1. This value should be greater than this value should be greater than this value should be greater than this. For designing transfer having step-down voltage, the value of K should be less than 1. That is, this is what is not less than this, less than this, less than this. Okay. For step down transformer. These are the two possibilities, important possibilities. There is one more possibility. That is, the value of K equals 1. The ratio is 1. So these are equals. When they are equals, the ratio is 1. If the ratio is 1, the transformer what is obtained is called as isolation transformer. The name is called as isolation transformer. There is a purpose of using isolation transformer. This transformer is used in highly sensitive electrical equipments. That is, equipments, the safety of electrical equipments is the paramount. Where there is the safety of electrical equipment is the paramount. Example, the places of hospitals, the places of industry, we look at what is the safety of the electrical energy you are using, high voltage as a low voltage. We are looking for the safety. That is why in that cases using isolation transfers. So let us not go detail about this. That is one, it is called as isolation transformer. So whenever the transformer is designed, the device is designed, we always look at the efficiency of its work. How efficient it works. It is called as efficiency. We talk in terms of efficiency. The efficiency is designed and is given by the definition. Output power, input power. Ratio of output power to input power. The power. How much power is transferred? Is total power transferred or only some amount of power is transferring? The ratio tells us. The power is defined by the equation voltage into current. Output power in the secondary coil. So it is the VSIS. Voltage and current at the secondary coil. Input power at the primary coil, and V and I are primary coil. So efficiency is given by these equations. Efficiency. If the efficiency is 1, it is known as 100% efficient. So transformer works at 100% efficiency. It is an ideal one. But in reality, we cannot have 100% efficient transformer or man-made device, because it's a man-made device. In reality, the efficiency is less than 100%. So there is always, after the device, the efficiency is always less than 100%. It is all because of practical difficulties. The materials defect that make so many causes are there inside. So let us discuss them in detail in the next session. Because of this 100%, but we can minimize the fault. We can improve the efficiency. So in the present day, we have improved the efficiency of the transformer to 95%. That is the best known one, of course. So this is about the power transmission, the power transfer from primary coil to secondary coil. In this AC current, as you know, is always in the form of sinusoidal wave current. So this AC current induces flux, variable flux. The variable flux induced in the material also has in the form of sinusoidal wave. This is sinusoidal wave. Look at that. There is similarity between the current, AC current, and flux in the magnetic field, magnetic material. And in the primary coil, we have both current and voltages. Both are sinusoidal wave. Already told in the previous classes. So one wave, that is voltage, sinusoidal wave for the voltage, and the white one sinusoidal wave for the current. The difference is phase difference. There is always a phase difference is pi 2. Current is always lagging behind the voltage because inductor. The coil is inductor by pi 2. That shows that phase difference between the white and yellow. And look at that, this pink color is a sinusoidal wave for the flux. It is same as current. AC current. Both are in the same phase. AC current in the coil and magnetic flux in the iron. AC current in the coil, magnetic flux in the iron are in the same phase. Magnetic flux also variable. So this is what the discussion about, the basic discussion, that is basic principle, the basic aspects involved in transformer, on what basis the transformer is designed. Here, power transfer from one coil to other coil without electrical connection through magnetic field. That's the design. That is, electric energy changes to magnetic energy, then magnetic energy changes to electric energy. That is the principal basic idea. So with this, let us wind up for this session. We shall continue with the next session. Thank you.